And I think we left off on what? What did we leave off on? Yeah, the dealing with the stack. We're not going to have any problems. I'll do a little more research on it as we move through. The 1100s does not support index addressing, but the 1000s and the 504s do. So that means we have no problem doing these labs on the PLCs that we got. I was trying to read up where it told you how to manage this with the 1100 the PLC, but I didn't quite get through that. So we were talking about something called a stack. So how would y'all explain a stack?
Stacks all the information. Oh.
Well, we know we have to we know we constantly have to move data around, right? One of the main things that a computer does is simply moves data around. The problem is that if I've got to come around and specify addresses all the time, it's going to be very, very cumbersome. We would like to have a place that the processor inside the computer, whether it's this computer or this computer, can use without me having to specify where to put it all the time or where to get it from all the time. And this is the function of the stack. So the stack, once we set up a stack pointer or establish a stack, we can use very simple instructions to either push data onto the stack or pull data off the stack, or the book calls it popping the stack, right? All we do. So when we use jump subroutines, so I use a jump subroutine. Well, the microprocessor has to automatically have access to some addresses so it can save the flag registers, it can save all the things inside the processor to handle the subroutine without me worrying about screwing up registers in the subroutine, right? You understand? And then when we come out of the subroutine, it can go and retrieve all that information. So it's a set of addresses that the processor can automatically do once we establish the location of the stack. And of course, the stack in the 504 and the SLC 504 and the MicroLogic 1000s is in the status register, right? S24, S224. So using FIFO, FIFO stands for what?
First in,
First in, first out. LIFO stands for last in, first out. Then we have an instruction that we push stuff onto the stack. The MicroLogic refers to it as load and unload. We could also call it push and pop, right? You understand? We could also use store and retrieve. So there's a lot of words that you got to get used to. Somebody asked in the other class, you know, which word are you going to use? You know, yeah, that's what I'm saying. You got to learn. You need to learn all of them, right? You understand all the words that's used to represent the same thing. Because when you start calling people for help on the phone and stuff like that, they need to be able to use all these words. You know? Like a comedian. What was his name? I don't remember. All I remember is said, "You can call me Ray, you can call me Jay, you can call me RJ, you can call me RJJ, but you doesn't have to call me Johnson." That's what he said. And that's basically what we're talking about here. So you have multiple names, and you know when they talk about you, you know, I can use any one of those names. And I fell into what my dad did. My dad used to get so mad at us, he'd start with one name and just go through them. He'd get so mad, his brain would go dead and he'd forget who he was talking to. And I do the same thing. The exact same thing. So we talked about the LIFOs and the FIFOs. We talked about loading and unloading the stack. We talked about the move with mask. Are y'all okay there? And what type of mask is that? Or mask, yeah. We have two basic masks we use. We use or mask and AND mask. AND mask we can use to clear bits in an operand. Or mask we can make sure that bits are set in the operand in our results. Move a mask. I think we actually did a little bit of that with Logic Pro.
So or mask sets.
Yes, sets bits. So if I've got a 1 in a mask, I don't care what's in what we're ANDing it with. So we got two things that we're going to deal with, kind of like we do with subtract, and kind of like we're dealing with adds. So a lot of our instructions deals with two different operands, right? And so let me bring up Logic Pro, and then we'll see if it supports these. So Logic, and what we'll do is we'll bring up an AND. So on these, and notice what it says, and even it says this on Logic, it says bitwise AND. So what that means is we're ANDing 2 bits at a time. Every bit in the unknown, we're ANDing with a mask. And then we got a destination. So source A, these can both be use the other addressing modes. We can use index for 1, but if we do that, we're going to use one. I'm sorry, immediate as 1, but the other one has got to be. It's got to be one of our register addressing modes. Okay, y'all understand that? Your destination has always got to be a register. Okay, a register address. We know we got different addressing modes available to us. So what we're going to do is we come up with a mask, then we're going to AND it or it or something with some unknown. And I think this is what we were showing y'all the other day. So I can come up here, and instead of me putting, so what I'm going to do on the unknown is I'm going to just come up here and represent this with X's. And X means they could either be a 1 or they could either be a 0. So these are unknowns. We'll split it up in groups of 4s. And then we come up with a mask. So let's say we just use this mask right here. Very simple. Okay, so this is my mask. Okay. And what would my answer be? Well, here we would get X, right? Well, first of all, we have to establish what type of mask it is. So let's say this is an AND mask. Here I'd get X. What would we always get here? Yeah, we'd always get a 0 because it's 1. And so if we draw this logically, we're doing this. One of them's going to be a bit out of A, and one of them's going to be a bit out of B. And this is what they're talking about bitwise. So that means this bit is AND with this bit. This bit has nothing to do with the bit right next to it, right? So that's when they put up there bitwise. That's what they mean. We do it. It does it what? 2 bits at a time. And that would be like me taking these 2 bits right here, if this is A and this is B, and bringing them in there. Now, an AND says we have to have all highs to get a high. So if any input is low, the output would be low. So here, is any input low? Okay, yes. Here, Yeah, but all we know is whatever it is, it's gonna come through. Okay, you understand? So if this was a 1, that would give me 2 1s and X would come through. If this was a 0, it would come through as 0. So whatever X is would come through. This right here would be a 0 no matter what, right? So this is actually what would actually come through in my answer. So what we're doing, what we're doing is we're making sure certain bits are cleared or zeros, right? You understand? Then we're letting the other bit come through, and these are masks. Now this is what we use our mask for.
Making sure the ones that we know are zeros get blocked.
Well, we don't know they're zeros. So what we're doing is we're taking an unknown value. So that's why I'm putting for X. And we're deciding what bits of X we want to come through. Whether it's whatever it is. So if I put a 0 there, what I just did is I blocked that bit. So I don't care what X is. Whatever X is, it could be a 1, it could be a 0, but my answer will always have a 0. If I come up here and put a 1 in my mask, then whatever X is comes through. Okay, you understand? Now, what if I did the same thing with an OR mask? This would always be a 1, this would be an X, this would always be a 1, this would be an X, this would always be a 1, this would be an X, this would always be a 1, this would be an X. Understand? Okay. This would always be a 1, this would be an X. So what am I doing here? So my AND bits, I'm making sure certain bits are 0. My OR bits, I make certain bits 1s. Right? Does that make sense? So they do the opposite thing.
All bits are looking for 1.
You can't say look at it, it lets 1s come through. If you say it's looking for 1s, what if X was a 0? Well, then it'll come through as a 0. What if X was a 1? Well, it comes through as a 1. So what we get is that with an OR, we can make sure certain bits in our answer is always a what? A 1. With an AND, we can make sure certain bits in our answer is always what? A 0. And this is what we was doing. If I was only interested in these 8 bits down here, how would I strip these bits off? Well, we could come up here and I could use an AND mask like this. Right, you understand? So this would be my mask. And then I would come through like this. This is unknown. Whereas, but my X's take up more room than the 1s and 0s. What would I have in my answer? These right here would be 0s. These right here would be what? No. They would be whatever my unknown is. Now, if I did an OR, y'all understand, then I'm on, these right here would be X's. These would come through, and these right here would be blocked. So no matter what's up there, we're going to get 1s. But it all depends on what you're trying to do. What do you need? What are we looking for, right? Whether you use an OR mask or whether you use an AND mask. Now, of course, the AND mask is by far the most popular because what we're doing, we're literally stripping off bits that we're not interested in, right? Okay. So that's why when they came up and gave this MVM instruction, this is a masked move. And it's an AND mask. But what this is going to do is going to serve 2 functions for you. It's going to do your move and it's going to do your mask in one instruction. But this always uses what type of mask? Yeah, AND mask. And this is where hexadecimal comes into play. You know, I could enter it in decimal, so I could say this was a mask of 255. But it's not a decimal mask. It is a binary. It is a bitwise mask. So it would behoove you on these guys to probably use hexadecimal, because hexadecimal is a lot easier to deal with than, so which is easier, for you to key in all this or to key in this? The hex is a lot easier, right? You understand that? And that's why we use hex. We don't use hex to make things confusing. We use hex to make it easy to deal with large binary numbers with very few digits. So when you do binary math on your calculator, if you got a scientific calculator, if you use hexadecimal and you get 13 digits, you can represent some big numbers. 13 digits worth of binary. You lose the most significant digit for the sign bit. So that means you only get 12. You get 12 bits, which would be 4,096. So that would be the biggest number you could represent on your calculator if you tell your calculator to do binary math. If you tell it to do hexadecimal math, then you're going to deal with 13 digits of base 16. You're going to be able to, you could actually represent bigger numbers and without going into scientific notation with hex than you can with decimal. So hexadecimal actually has a better resolution than decimal. Binary is very poor because each digit only has how many combinations in binary? 2. How many can a decimal digit have? Every decimal digit, how many combinations can we have? I say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many is that? 10. It's the base of the number system. So every digit of a decimal number system can only have 10 combinations. How many combinations can a hex digit have? 16. So it actually has, so I could represent bigger numbers with a hexadecimal with less digits than I do with a decimal number system. Which is pretty neat. I was looking at the stack, first in, first out, last in, and we use those instructions, right? Primarily uses indexed addressing. I need to figure out what it does on this guy. This guy right here doesn't support indexed addressing, which is very, very strange. But when you look at the instructions, it shows the index addressing. So I'm gonna have to do a little research on the 1100 MicroLogic 1100. But both the SLC 504s that we have and the MicroLogic 1000s both support index addressing. We'll see if we can find this program right here and see if we can see what's going on. So here we're using, what addressing mode are we using here? Index. All right. So this is B3. This is our data file that we're going to be using. What's this right here?
Word. That's what. Offset.
Offset, right. So what we do is to find the actual word address, we would add the offset to the contents of the index.
Right.
So right now, we don't know where this is going to go, unless we know the what. Unless we know the contents of the index. Everybody understand that? So this is the part of index address. This identifies as index. This tells us what data files we're going to be using. So we're going to be using addresses within the B3 range, right? You understand that? This right here is our offset. Okay. What's this one?
It's intermediate.
This is not immediate. This is direct address. We can't do immediate addressing with an output port. So all your output ports are direct address. Everybody understand that? So this is says we're using what? Output. This says we're using output number 2. Right, you understand? This is our control register. This is gonna keep up with the status bits that's going on. And we're gonna push how many bits? 3. Okay, everybody okay? And we're gonna start at what? Position 0. Okay, so let's find this one and see what we can do. What I'm gonna do is I'm gonna bring this up and go into program controllers. Let's see, go back one. Logic flow diagrams. And this, y'all find this in your book and tell me which figure number it is.
14.6.
Oops, wrong class, Rich. Says it's already running. It is. It is coming in. Okay, so here we go. So what do we need to do? So we're going to start off counting. We're going to take the contents of the accumulator and push it onto the stack, right? We're going to use B3 with an offset of 0. So let's look and see what we got set into the stack pointer. We can put, how do I access that? I'm going to come up here. On this one, we can hit this right here. On your other PLCs, you would come up here and pick this register right there, right? And then we're looking at what? S24. Now on your MicroLogic PLCs, it's going to pop up the registers that you don't control. I mean, that's used automatically. So if you're on the 1100 or the 504 and you bring up the status register, S24 is going to be there. So you won't have to go down through this thing and look for it. So here's S24 right there. So right now we're using what in our index register? Oops, sorry. Okay. So what do you want to put in there?
Put a 5.
Okay. So let's see if we can do it from here. We'll try. If not, well, yeah, it looks like it's going to let me.
12.7.
Oh, thank you. Well, I should sit down. Thank you, Kevin. Here's 24 right here. So Vincent wants to put a 5 in here. Now this is an addressable register, so what you could do before you used it, you could literally go in and move something into it, right?
What's that? 3 put in?
Not put a 5, hopefully.
A 2 and a 1? Oh, I thought you put a 4 and a 1.
No, that's a 4,
Oh, okay.
and that's a 1, that's a 5.
So you don't worry about the number.
No, these are bit numbers. This is 2 to the 0, which is 1.
Okay.
This is 2 to the first, which is what? 2. This is 2 to the second, which is 4.
Okay.
So we got a 5 in there. So what we're going to do now is we're going to go to our B3 registers. And where are we going to be at? Well, we're going to start at what? Well, we're going to start at 5 because we got an offset of 0. So we put 5 in our status in our index register, right? Are we okay? We okay? So when we start this thing up, we should go. I don't know why they got 1,000. We should go 0, 1, 2, right? So let's see if this is gonna work. So let me find my way back home. So download and we switch it to run. And what we'll do is we'll bring up our IO simulators because no, they're not doing anything. Dang it. They're not using the output of this thing. So what we'll do is we'll just monitor that status register. Okay. I did download it, right? Well, I'll do it. Don't hurt to do it more than once. Okay, what it is that, this guy right here is gonna count for us, so let's change it to a push button. And then we decide when we load and we decide when we unload. Okay, we're gonna use input 3 and then input 4. And then we'll reset it with input 7. And input 8 is gonna okay. Alright. So we're running, right? So here's my counter. Okay, and then we'll come up here and we'll push this onto the stack. Okay, so it should go 5, right? Because we've got an offset of 5. So it should go right here. Let's push it. That would be this guy right here, or load it, right? Huh?
Oh, you gotta keep on.
Well, no, it should have pushed the first one on there. When I came over and hit this guy.
Oh, you had to make the left first, I guess.
No, but he should have went at 5. Let's see what happened. Let's go over and pull them off. So it did. It started at 0, but we thought it was going to. Let's go back and see what happened with the status register. What we might have to do is we might have to load that with an instruction. The stack is 24, right? Yeah, so it went back to 0. So it went right. See, it went back to 0. So we'll do it. We can't do it with this guy. This guy don't have a stack pointer on it. So let's reset everything and start over. So we can't put a 5 in there, Vincent. Okay. Okay. So let's come up here and make our counter count. 1, 2, 3, 4, 5. And then we'll go into the B3s. Okay. Let's say we'll push it on there. So this loads the stack, right? Okay, so there's 3. Can you see where it went? It's the top of the stack. Then we'll come up here and we'll put another count in here. And then we'll push this. So we got a 6. There's a 6. See that? Yes or no?
Wait a minute.
Where you got the 6 at?
6 went right here. We're using
B1?
a first in, first out. So notice what's happening. The 6 actually goes here.
Okay.
So what we're doing is we're filling it coming up this way, right? So here's the first. Here's the 3 that we pushed on there. Here's the 6 that I just pushed on there. Are we following it? So where should the next one go?
Yeah.
Should go there.
Put 9, it should show 9.
Well, I'm putting a 13, 14, 15. We'll put an F in there. And we'll come up here and push it on. Okay, so it went right here. That right there.
Right.
Now, what I want you to notice is I'm not changing the address. It's automatically doing what? It's automatically changing it for me. So I can come up here and just, without me having to specify an address, I can just keep pushing this thing on there, and it automatically goes to the next location in the stack. Right? Everybody understand?
What am I using it for?
What we use the stack for is, I'm trying to save a bunch of information. And we want to go out there and we want to put this information in consecutive addresses. Well, if I use regular addressing mode, I would have to, if I wanted to save 256 bytes of information, and I wanted to do using our other addressing modes, I would have to have 255 instructions. Each one of them going 1 bit at a time. So first time I might save it at bit 0. The next one I would have to specify bit 1. The next one I would have to specify bit 2. The next one I have to specify bit 3, right? I'm sorry, word for it. Well, what we do with the stack is if I'm trying to save I'm trying to save a bunch of information. Okay. Let's say I want to go out there and I want to read my count out of a counter every 15 minutes. Well, but I don't want the last read to wipe out this read. So what I'm trying to do is I'm trying to keep up with my count over a 24-hour period. But I want to see what count I have every hour. Okay. Well, if I use the same address every time to save it at, the one I just stored is going to wipe out the one I just had, right? You understand? So what I like to do is I would like to have one instruction that would automatically, every time I do it, it's going to take the contents of my counter and it's going to save it on the stack. And next hour I would come up and do what? Take the contents that use the same instruction every time and it would automatically go to the next address. Now that's putting it on the stack. But sooner or later I'm going to have to do what? I'm going to have to unload it, right? So we need to have the ability to unload the stack, right?
So for my down the line, I got 6 counters.
Well, we'd have to have a different stack. Well, we'd have to have a different stack for every counter because you've got different sources now. What we're doing is we're using the same source, right? You understand so every one of these are using the same source. This is using the same source. It's using the accumulator of counter 5. So I'm taking the accumulator of counter 5 and then I'm doing what? I'm pushing it onto the stack. Okay. Everybody understand that? Now, when I pull them off, look what's going to happen. We're using the index address again. Here we're going to unload the stack, but here we're going to output them to what? To output number 2. And of course, this is output number 2. This is a first in, first out stack. So what's going to happen is when I unload it, that guy's going to go to an F over there, right? You understand? And then the next time I unload it, it's going to do what? It's going to do this. The next time I unload it, it's going to do that. Okay? So what we're doing now is we're pulling it off the stack. So when we pull it off the stack, we have to say, okay, this is unload, right? First in, first out, unload. We specify the same index register. We say we're going to put our output where? 2. And then we're going to have a length of 3. We're going to start at position 3.
Okay, you said we have a length of 3.
Yeah, you have to specify the length of the stack. Now, what's going to happen, most of the time when we specify the length, what should happen is that it would keep going, but it's going to give us a bit indicating we filled our stack up. But odds are it's going to keep going. Y'all understand that? It's kind of like a counter. So a counter, when it hits its preset value, does it stop counting? No. It keeps counting until you do what? Until you reset it. So when we specify the length, what we would do is we would go to that R register and we'd figure out which one was the done. In fact, let's see if it gives us a, in fact, this one gave us a what? Done. Okay, so now let's unload it. Now here we're going to send it to an output. Okay. I thought that was going to go backwards. First in, oh, that was first in, first out. Sorry, so let's reset it. So we anticipated wrong. I don't know why they're resetting each one of them done. It is. So here we're going to push count. What's our first count? 15. Oh. Okay, it's 18. I messed up on my button. So here we're going to load in an 18. Okay. That's the top of the stack, right? Then we'll come up here and increment it a couple more. Push it. That's going on the stack. Come up here and push this next one. What should we have? What should we get now? Should get it done. See that? Now I can come up here and push another data, so it's like a counter. No, it don't. This one don't do what? I was wrong there too. This one did what? It stopped.
So
I'm listening.
I don't know how to see it. On the count, okay. At what point does it go into the low? Like, you started on count 16, I didn't see anything.
Until,
Push the button.
so this control, when I'm gonna push it on the stack over there.
Okay, so you
So I've
would
got
just,
to hit button 3, push it on the stack, so I can go whatever count I want to, up to 1,000.
and then you start pushing and you want to push whatever.
So what I'm doing is I'm pushing stuff on the stack, and this is a first in, first out. So who is first in? So this is first in, right? You understand? So when I execute the unload, you should see this, right? You understand? Then it should be what? This. Then we should see this. So here we go. So there's my outputs. And notice what happened to the stack. It automatically unloaded it, right? You see that? This turned to what? Zero. What's going to go next? This one, because it's first in, first out. So this is the next one that's in line. So here we should turn on all the opposite lights. I did that backwards. Yeah. This guy right here, this is top to bottom. Yep, I'm getting this. And so this will be next. I'll keep going to the bottom. But on this one, okay. So let's clear everybody out. Okay, clear this guy out, clear this guy out. Okay. Now we didn't clear the output, so this is going to keep whatever's in there. So right now we got a count of what? 22. Okay.
Why are we not back at position 0?
What do you mean?
Because we got some stuff
You
with
can
that.
reset the count.
I reset this. So let me come up here and do it again.
We set the register.
So there's no reset on the counter, by the way. We would need to put that. Are we okay? So we got 22. We come up here and push it. Okay. There it is, right? Didn't we push it? Now we got 1. So let's go up here and put something in there different. What do you want to put in there? Okay, so here's 9. Okay, so we're gonna come up here and push it on the stack. Okay, goes on top. Okay, there's 9.
Okay, one pusher pushed that 9 on the stack. Okay.
Whatever's in the, so what we're doing is we're taking whatever's in the counter accumulator.
Yeah.
And when I push this button, whatever's in the counter accumulator is pushed on the stack.
Ah.
Okay. Then we can come up here and do whatever we want to. What do you want to go to next? Oh, so there's 15. Okay. We'll push that on the stack. See, all ones went on the stack. Then I'm going to come up here. And then we'll come up here and put another number. And then we'll push this onto the stack. Okay? So let's get this right. Which one on the stack first?
One at the top.
The one on
0.
Yeah.
Okay. First in, first out. So the first time I pull it, the light should turn on at a 9. The next time it should do a 15. And this right here should do. So here we're going to pull it off. Here we're pulling it off the stack. Okay, so there's 9, right? What's going to be next? 15. Oops, this guy right here, right? There it is.
31.
And 31. And now the stack's empty. By the way, as soon as we got rid of 3, both these guns went off. So we don't have to pull everything back off. We could pull one off and then start pushing more stuff on there, right? If that makes sense. So your done bit, and this guy, I did that wrong. I thought it would keep going like a counter, but it don't. Once you hit this, it does what? It stops. The stack is full and it won't let you push it.
So what's the length? mean,
That's the length. We said, okay, we're gonna push 3 things on. Now, these right here should match.
okay, 3, okay, yeah.
So how many would it let me push?
3.
3. As soon as I push, we'll do 3 of them real
You do
fast.
4, it won't go.
So here we'll come up here and just load the same thing. So there it is, there it is, there it is. Now the done bit's gone, and now I can come up here and do this all day long. They won't let us do it. Yeah, so we can take it out of run and go to program. And this is a variable right here. So we can come in here and make it. Yeah, we can change it to 4, right? Okay. And change this to 4. It automatically changed. And then we can download it and reset it. And it's going to start at position 1. We'll put it here. So let's reset these things. And so they automatically jump back, sorry, to position 1. 0. And now we should be able to do 4 pushes. So let's just throw something into our counter and we'll do the same thing every time. So here's push, right? Okay, sorry. Let's bring up our registers when I took it off it. Then we'll do a push. Oops. And a push. Now we went to 4 and now we got a what? We got it done.
What 4 is on?
It is kind of the 2.
This is 4.
Oh,
You're trying to use this right here, but this is a bit number.
okay.
And it's actually, it goes 1, 2, 4, 8, 60, 30, 64, 28, 65.
I was going down, I wasn't seeing 3. I'm going from 0 to, you know, and I only saw 3, but my eyes.
Oh yeah, I see what you're saying. Yeah, that one's kind of run together.
So
what we can do though, what I want you to know is that we're loading, and how far could we go? Well, we could use the whole V3 register. In fact, I think we could probably we would have to go look at that.
That'd be what, 16?
Well, it'd actually be 256 different bytes we could have in our stack if we use the V6, if we use the V3 register. So we could have a length of up to 256.
So what are we gonna look at in our R6 register?
R6. So the book doesn't define that. So what we'll do is we'll go in and we'll bring up the data and see so the book does not define R6, what's going on with R6, but R6 is a status register, right? You understand? So we're going to have probably overflow and that kind of other stuff. But let's see what actually is in there. So what I'm going to do is I'm going to go and I'm going to look up the actual true manual for the 504 processor. That's the control register, but every bit is going to have something. Does it tell us what the bits are? Yeah, but it's a different thing. The bits might be the same. So what we'll do is we'll look and see. We'll actually go to the data. So programmable from ClassRich. Advanced PLCs, manuals, Allen Bradley, and then the 500 instruction set. And we're dealing with first, yeah. And what we're doing is we're looking and seeing, so here's the picture in the book, works out pretty good. And what we're doing is we're looking for the status register bits. And somewhere in here is going to give us an explanation, hopefully. Addressing using updates, using indirect addressing. Enter mass values. No, I'm in the wrong. It didn't. No.
It said that they enabled this in the done bit. So they control the rest.
Well, we know we're going to have these 3 bits right here. We know we're going to have a. We know we're going to have at least 3 bits that are displayed out here on the. Yeah, we know we're going to have an enable and done. Okay. Enable should flash every time we hit this push button over there. Dunn is gonna, go as soon as we match our Mitsubishi product. I didn't know that guy was up there right there. Yeah, so we got three, and we looked them up the other day, but I just can't remember what they are. Somebody asked the
That
question.
was empty.
One of them is empty,
That was done.
this is empty, EM is the same on both of them. You remember what that is?
Yeah, it would be.
Enable and one was able.
Take it,
I wrote it
EM
down.
is empty, EU is unloaded,
Thank you.
and EN is loaded.
That's what we wrote down the other day.
Yeah.
So did y'all hear? That's what we went over. We found it in the book though. And that's in the R, what register are we using?
S
R6.
R60, right? So here's R60. So we'd be looking,
You got position,
Position for her.
you got your length for the 4. But your done ain't done. Well, done is done, it got 1 in it, yeah.
yeah, so it's done right there. Now it's up to you to monitor these bits, right? If you want to do something, if you want to do something when this thing is done, then you just kind of like you do with counters and timers, you know, when you can do done bits and stuff like that. That would be up to you to use the instruction.
Okay, can we see it? What
It'll
word
be
like
labeled as R6.
Oh, you mean the status register work?
Yeah.
Okay, well, we'll just push the same thing every time. So we're in run right now. So let's come up here and reset everything. So this resets. And then we'll come up here and just put something in the counter. So we should have got empty.
Yeah.
Right. So right now the stack is empty. That makes sense? So EM means it's what? It's empty. So as soon as I push something on the stack, then we're no longer, the stack is no longer empty. Right? So we got no problems. Come up here and load it again. Still nothing. Now notice the enable goes true every time. Okay. Now hit it again. Enable. Hit it again. Now we're what? Done. Yeah. Now when we come over here and we so here we're pulling. Okay. Here. Now notice the enable on the unload is going true now. Okay. Here, and now we're what? Empty. Now the stack's empty. So this bit would tell us if the stack is empty. This only enables when we enable the unload. That one, every time we enable the load. Both these click on at the same time because they're going to both be what? Done at the same time.
I don't see that. What you said, EM? What
EM means the stack is empty.
EM is low.
No, EM means the stack is empty.
EU is unloaded.
This is EU is unload enable. EN is load enable. DEN is what?
Done.
Done. So this bit right here would tell us when the stack is full, right? This would tell us when it's empty. Can't get my phone up.
Well, it's sort of like, done, that empty and done.
Yeah, it's just like, it's just a stat, it's just bits that you'd look for if you were gonna deal with a stack. And what's nice about a stack is if I was gonna store the output of my counter in multiple locations, in 4 different locations, then what would I do? I'd have to have a move instruction. On this situation, I'd have to have 4 move instructions. But then I'd have to figure out how to do what? Get them suckers back off.
So to get them back off, I'd have to have 4 additional move instructions, which goes to those addresses backwards. So what we have with the stack is we got a place where we can just use one instruction, say push it on the stack, and later on we can do what? Pull it off the stack. So it's just like a restaurant when you go in there, when they got all them plates in that thing, not a restaurant, like a salad bar or something. And that's a stack, where they got their stack of plates. They know they're gonna need a lot of plates, right? You understand that. And instead of putting them all out like this, which would be consecutive addresses, they automatically do what? Just stack them off. But we have the ability to pull them off the bottom of the stack or pull them off the top of the stack, depending on whether we use a first in, first out, or a last in, last out. Last in, first out. I'll take a break.
So the next example should be last in, first out. So I'll pull that one up while y'all.
Okay, for the bay.
So what's the LIFO? I guess, what was this one? This was 11:4. I got my book right here. $14.9 is the LIFO. So there's a file field. They have a, okay, there's the LIFO. It's on 14.7, right? We need to move on. We need to finish these today, so we need to. Oh, here they're gonna take an input 3, so we can put anything we want to on this one instead of using the counter, and then we're gonna load them from input 3.
Can you pull from the middle of the stack?
Not with the first in, first out. You can't pull or push from the middle of the stack.
Do they have one?
Well, you've always got access to your move instructions. So if you know your stack is 16 bytes long and you know where it's at, then you can access it using any a move instruction, or you can access it using a math instruction. So you can it's an address. I mean, it's an address. Understand? So you can address access. You can address memory locations using any of your addressing modes. It's just that here, if we use the push and the pull instructions, it automatically does it, but you can only get them off in a certain order. So that means you go to some place and they've got a pile of plates up there. You can get the middle plate if you want to. I mean, it might be a little hard, but you can still get to it. You know. I think we brought that up last class. That section right there. Are we okay? Any questions? Okay, so what's next?
Copy file, fill file.
Yeah, copy file and fill file. Data handling instructions used to store blocks of data into a data file. So COP would copy a group of data into a lowercase copy from. Bill would do what? Now, tend to use these instructions to manually enter a file with a constant number of data from a file. So this gives us the ability to just shift data around, move it from, do what? Take it from here and move it to there. So this would be kind of similar when I come up here on Windows. And of course, you can understand, we constantly move stuff around, even here, right? You understand that? So I constantly can come up here and go to any file, and what can I do? We can move it, but here we're gonna do what? Copy, right? And then what would we do? Then we're gonna go to somewhere else, and then we're going to what? Here they call it paste. So what did I just do? I copied a file from one, and this is a lot of information from one place over to the other. So this is what this guy right here is going to do. It allows us to move a block of data. So this is a block of data, right? You understand? Occupied a lot of space inside on my disk. Here what we're going to do is move data around inside the memory of it. Now to move it, what would you have to do? Well, to move it, what you would do is you would copy it, and then you would come back and delete the original. That's what we would have to do here. I'm not going to delete my original. I'm going to delete my copy. So we do this all the time. So if I'm doing it with my computer and I'm doing programming, then odds are sooner or later this is going to be something we need to do. So I can just take a block of data out of the V3 registers and move them over to integer registers or something like that, right? Does that make sense? I personally have never used it, but I can see the need for it. Does it give us some examples? That's where the book just leaves off.
It's got a field instruction.
Huh?
It's got what they call a field instruction.
Yeah, field instruction. This is in 14.9. So, do that all the time. We don't have 14.9 yet. I don't have 14.9. It goes from 14.7 to 14.11.
That's not being important.
Let's not. But y'all understand it? Y'all okay? Yes or no?
Page 3 or 4.
Yeah, 14.9 is the actual figure that they've done. And this is, and so this is what this has provided us. We don't go in here and do all this. So I probably need to make a note. So we're looking at 14.9. That's the example the textbook gives for filling and then copying. So what are they going to do if we I didn't bring my camera out, guys. I'd bring this up. So it looks like every time we hit input, it's going to
Take the source 5,000 index register in 7, which is length of
10. So what it's going to do is it's going to put 5,000 into all of them. So here we're doing immediate addressing. We could use index addressing and automatically take it and actually move it, right?
Yeah, it's got a time on it.
Yeah, a timer when it times out. And then it's going to reads data 5 from input 2. So the next section is probably the best example. So what we're going to do is we're going to do what? We're going to take what's in my input 2, and then we're going to put it using index address, and we're going to put it into V3 with an offset of 0. Right?
Right.
And how long is our file? 5. Okay. So every time my timer times out, whatever I have on input 2 will go into this file. Right? So how long? Every 60 seconds. Right? You okay? And then when I do input 1, what's it going to do? it's gonna copy what I just did. It's gonna do 20, automatically gonna do 20 bytes. Y'all understand the beauty of this? Yes or no?
Go back over it. Let's do it again.
Yeah, I wish I had my camera. I do have this camera right here. Ah, dang it. I can't do that. So let's look at run 3. So what's going to happen when I close switch 1? Input module 1, switch 2.
The index, N7 is gonna go to the index E10 for destination.
And how many words is it going to transfer? That one instruction, how many words is it going to transfer? 20. Y'all understand that? So what we're doing is we're using one instruction to move a block or copy a block of 20 addresses with one instruction. Y'all understand that? Yes or no? Huh?
So with the field, we're filling a register.
Right.
And then with the copy, we're gonna copy from the register.
Yeah. Not from, a group of storage locations. Okay. Which the book uses those terms interchangeably, which I don't like. But I find myself doing it. So we got all these data files. So what we're going to do on a field is we're going to fill a group of data files with what? Something. Right? You understand? So this is going to start at using index address, and it's going to start in integer register 0. Well, I'm sorry. 0 plus the index register, right? Okay. And then it's going to automatically grab 20 addresses out of the end register and put them where? It's going to put them in the B10 data files. But we're going to move 20 bytes or 20 words worth of information with how many instructions? Or not move, copy with one instruction. That makes sense? So it's just like me when I come up here and do this, you don't have a link, but this would be an instruction. So I come over here and I right click on that, and let's look at the properties right here. Well, the properties said that this instruction right here is 91, this file contains 91.5 kilobytes worth of information. Now, if I was to go in there and have to move those things a byte at a time, it'd take a long time.
Maybe a year.
Well, what can I do?
Just copy the whole.
Yeah, what I can do is I can come up here and I can right click on that, and even though it's 91,000 bytes of memory, I'm going to be able to say copy, right? You understand? And then I'm going to tell it where I'm going to put it at. Then I say a what? Paste. Now, there's a lot of addresses out there on my disk drive, and disk drive have addresses just like your memory has addresses. We call them allocation units. So an allocation unit, what it did is it automatically went out and did what? Pull those allocation units out, even though I didn't specify. All I said, start with the what? Start with the first one, but it automatically knew to do what? To go out and get 91,500 bytes worth of information and then copy it. But how many instructions did it take? Took one. Took my paste. That was the paste. So the paste is the same as the copy. The field would be basically where we select the data that we want, right? And then, so which is pretty neat. So I just didn't do a move, I did a copy. Now, of course, if I wanted to move it, I would go back and delete the original. So if I do this with my computer, if I move data around with my computer, so it's just like the memory that runs this display. We're constantly moving information around to run the display. In fact, of course, right now we're doing the same frame, but when you're watching video, what you're doing is you're taking individual still pictures that we call frames, and you're moving it into the video memory.
So you're taking them from over here, from your game, and constantly doing what? Moving blocks of data and moving blocks of data. So we got to have instruction that allows us to move or fill blocks of what? Data. Now in PLCs, we don't use it that much, but it's available to programmers, right? And sooner or later, a programmer is going to need to do what? Need to do this, especially when you start communicating with other PLCs. So you're going to take all this data here and do what? Send it. So, well, let's say I want to send it to my computer, a computer somewhere, or an HMI panel, right? Up there. Then we're going to move blocks of data. So moving blocks of data is just one of the standard things that computers do. Especially on this, you can really see it going on here. You know. So I'm coming up here, I'm doing this with my little mouse. Well, what's it having to do? It's having to move blocks of data to reorient where those pixels are turned on, right? So we're constantly moving. These guys here are constantly. And this, by the way, this is the biggest bottleneck of the computer right here is your video card. How does it handle moving those thousands of blocks of data?
So this HMI and there's another thing called SCUDA. You ever heard of that? SCUDA?
Yeah, but they got different names. If you're talking about the HMI panels,
Yeah.
Yeah, Alan Bradley calls theirs a panel view.
Okay.
So I'm sure they're just different names. But normally they just take information from
Taking in data and stuff.
data, but you can understand why I would want to move information from one PLC maybe to another, you know, or from one PLC to a computer somewhere. And so we have these data files where we can move them into a location where that information is accessed. And like I said, this right here, so I'm going from memory in my computer to memory on the video card. So all my processing is done inside the memory of the computer, but now I got to take that memory and get it up to the video card, right? You understand, determine which pixels are turned on and which pixels are turned off. And man, there's a lot of them. So just to update the screen on this computer, it takes 32 bits of information, 16 bits to specify a pixel, and then 16 bits to specify the color. So if you go to, we could actually do some neat stuff, but I'm not going to do it. What am I doing? Over here. So when you come up here and you specify a screen resolution, so this is how much memory is required to update the video screen. You just take 1024, multiply it by 768, and multiply that by 2. If you're using 16-bit color. If you're using 32-bit color, then it's going to be times 4. And that's how much memory it would take. That's how many bytes of memory it would take just to update the screen on this computer. So you're talking about moving what? A lot of data. A lot of data. You do the math. So 1024 by 768, that's the number of pixels.
Then multiply by 2.
Then multiply it by 2 if you're using 16-bit color, which would be 65,536 colors. If you're using 32-bit color, which would be over 4 billion colors, which you can't see anyway, then you're going to have to update times 4. And that would be how much memory you would have to move around just to update the screen. I was trying to see, I don't know where they specify the number of colors here. All we're doing here is doing the number of pixels. We probably have to get into the display settings. And of course, the ultimate goal, so the computer would be faster the less number of colors you use, but the less number of pixels you use. So if we drop this down to the next resolution, everything's going to get bigger for one thing, but now my computer will run faster. I know that, right? But then we use that high definition. Well, copy files, I don't know if we'll have time for me to enter that in. I'll try that. Data conversion. This is when we convert from one system to the other.
So the primary conversions we have, of course, is taking BCD, going to what? Binary to BCD. Should have the ability to go from binary to ASCII, or from BCD to ASCII. Should have the ability to go to different types of formats. I think they go from, some of them support radians to degrees, and we talked a little bit about that the other class. Some PLC support that. So when you get into this, just about all of them does that to digital, and then decimal, and decimal to binary. TOD and FRD. So TOD is what? This converts binary to BCD, which we consider to be decimal. Everybody okay with BCD?
What is that for?
Two decimal. And FRD stands for from decimal. So we got two bases, and I want to send information to a BCD display. This is very, very common. You have to understand, we live in a decimal world, right? I understand decimal. So if I was looking at an RPM gauge and it said 3F73, and that was the speed of my motor, what would that mean to 90% of the people out there? Mean nothing, right? You understand? But if they came up and said 568 RPM, now that is decimal. So most of the time when we deal with sending information out to the standard person, numerical information, then we're going to send it out in a code, right? We call it BCD, binary coded decimal. So if I send information on temperature, the computer loves binary. Oh man, it loves binary. The problem is people don't understand binary. So that means when we start sending information out to the outside world, then by George, we better be able to use other things besides binary. So we have these codes, right? You understand? We have BCD, which is binary coded decimal. So we take binary. So every nibble or every 4 bits of hex has 16 combinations. But the problem is the decimal number system only has 10, 0 to 9. So what we do is we use the basic format that we use hexadecimal, but we trash 6 combinations. So we'd use the same patterns. We'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're through for using BCD. Right? You understand? So there's no such thing as an A, a B, a C, a D, an E, or an F in the BCD number system. But it is a code. It is not weighted. But now I can send this information to displays. I can send it to different things. And instead of this number popping up, it makes sense to me. And it don't work, by the way, this doesn't work on LogiPro. So notice we've got this display over here. This guy right here. Okay. And by the way, this is a hex display, so we can make this thing. So we got a number, so this is good. On 305, that's figure 14.6. It was 14.6 wasn't there. Jesus. Because the next one was actually 14.7, right? But this guy's very, very small. It won't take us long to do this. So let's switch back to here. Let's go to new. And it really don't make any difference what we choose here. We'll choose one of the MicroLogics because we don't have to enter inputs. And so what's the first thing we're going to do? We're going to use we're dealing with our data instructions. Where's it at up here? I know it's not control. It's not there. Guys, maybe that's why they don't have them. So here's timer counters, here's input output. This is compare. No, it's not there. Here we go. So they got it inside the math instruction. So we're going to do a 2
BCD, right? And then they're using a switch. They're using, let me go ahead and pull the other one down while we're here. By the way, Logic Pro will let you put a command inside the N wrong. So, I mean, it's a real good program, but, and then we need a push button right here. We need a push button right here. And then those were in the math instruction, right? Here we'll use N /0. Here we'll use N :1/1. And then what are we going to do with this? We're going to send it to output. Okay, so here we're going to take an input. Okay, our source is going to be what? Well, let's make it an input. Let's make it one of our inputs. Which inputs? So let's bring it in from our BCD, our switches. No, we can't do decimal. So let's bring it in from input 3. So our source is going to be input :3. Our destination is we're going to put this in a no, let's put it in an integer register, because what we're going to do is we're going to rip it off and we're going to put binary in and get BCD out and send it to our display. How's that sound? So I'm going to come over here and send this destination to N:0. And over here, we're going to take N:0, and we'll send this to our output. We're going to send this to our output that's got our display over here. Output, oops, put 6. Okay, so what we'll do is over here, we'll put in a binary input. And what should it do? No, this is not what I want to do. So let's get rid of this. Okay. So what we're going to do is we're going to input from switch 3. This is going to be binary, right? And let's change our destination to output : and 6. So what we're going to do is we're going to input something from this set of switches right here. Did I do that right? Yeah, I did. Input 3. And then we're going to output it 6. But we're going to take 2 decimal. Okay, y'all understand that? So what I've got over here in binary, I've got, so let's do a simple one. So this is 15. That's 15. But that's 15 in what? Yeah, well, in binary. It was 15 decimal, but it's, okay. So let's upload it and see. But our display should display what? So we're taking that input, we're converting it to BCD, then we're sending BCD out to output 6. So over here it should display 15. Okay. If it works. I've been having problems with this on this. So this is hex over here, 21. We actually inputted 15, right? Understand? So I can come over here. What do y'all want to put? So this right here would be, so it'd be 1, 2, 4, 8, 16, 32, 64. I'm going to close that. That's a binary 64. But when I come over here and do this input, it's going to display 64. So notice I'm putting only one switch is closed over here, but it took this 64 and outputted the BCD for what? 64. So what I can do now is I can take a memory address or take something. I can come up here and do this, and it's going to automatically send it out to my display in BCD. So that's BCD. So we're taking binary and this one instruction is converting into BCD. So I might have a counter that's counting our revolutions per minute, right? And then my counter is not going to count in BCD. My counter is going to count in what? Binary. But when I send my RPM over to the display, I don't want it to be in binary. I want it to be in what? In BCD. So all we would do is just take our source would be the accumulator of the counter, and then our destination would be BCD. Or if I wanted to count, we could do that. So we could change this real quick and add a counter. So I want to add a rung. I want to add it right here. Oops. So this would have probably been better. Okay. So what we'll do is we'll take this out and we'll do this instantly, and we're going to come up here and put a counter in here, just an up counter, and then and we'll simulate some type of sensor out there. So we input 1/0, okay. And then we'll call it P5:0, right? Preset it to, what do you want to preset it to? Yeah, no, we'll reset it. Now where my source is going to be here? It's going to be C5:0/ATC. And we're still going to send it to our display. Okay, so this is what my employee is looking for. He's trying to keep up with the count. Now, hopefully you notice that the counter is actually counting in binary. Of course, it looks like it's counting in decimal, but it's not. And what does it do? Yeah, I should have. Oh.
Okay, that's 23.
Yeah. This is, so there's a problem with the software. Believe it or not. I ran into this before. It worked okay to start off with, right? And then it switched back up, then it switched over to hex, by the way. So this is actually the number that should be displayed right here. Yeah. But what did so it's a problem with the software. So we start off okay. No, it didn't. Dang it. Thought if I downloaded it again, it would clear the counter out, but it didn't. So this is the problem with Logic Pro software. I've tried to set up an RPM thing for y'all, where I was simulating RPM with that register that's flashing at a certain time. I can show you how to do that. But the dang thing keeps displaying hex. It don't. So the problem is it's having problems with the what? Yeah, this right here. So what should actually be up there? 24. So the instruction looks like it's working, but when he wrote the software, for some reason, he's actually displaying hex. And we'll see if it's actually doing that. So it's displaying this number right here instead of what? So this is actually the BCD right here, 38. Y'all understand? And so I had a real neat little program where I was going to use this to run an RPM gauge where my counters count, and then you count for, you use an encoder. I wish I'd have brought an encoder. Y'all know what an encoder is, right? Y'all know what an encoder is? Yes or no? You okay, Alfred? You know what an encoder is? What we do is especially when we do speed and position, we don't want to count. So if speed is in RPM per what? What does RPM stand for? What does RPM stand for? What does RPM stand for? Good gracious, guys. Y'all killing me up here. It's like revolutions per minute. So motor speed is given in revolutions per minute. Well, by George, if I had to wait a minute to update the speed, so if I had a counter and I made my counter count for 1 minute, so I put something out there that gave me 1 pulse per revolution, and then I let that thing give me 1 pulse, and I counted it for 1 minute, and I displayed that, then that would work. But my RPM gauge would only update every what? Every minute. So what would we do? Well, what we would do is we'd put some sensor out there that has a lot of stripes on it. If I could see things more. So we have these encoders like this. And then we have a reader out here that sits here and reads it, and this thing is spinning. But now instead of counting every revolution, now I can count for seconds. Right? You understand? So let's say I have 32 pulses. So that means I'd get 32 pulses for 1 revolution. Right? Does that make sense? So I get 32 pulses per revolution. So what I could do is I could take my count, and then I could divide it by the number, and then I multiply this times 60. So this will give me pulses per second. Then I multiply it by 60. I would divide it by 60. And then this would give me, then I would get pulses per minute, right? So this would be an encoder. So an encoder is just a device that gives me it's a circular device that we would hook up to our motor. In the old days, we use generators. And the amount of voltage that the generator puts out would be dependent on the speed. But then if I bring that into a computer, I've got to take a voltage and convert it into digital. So now odds are when you're reading the speed of a motor, you're not going to use a generator, you're going to use an encoder. And that gives you digital out, right? You understand? So it's giving me pulses. My pulses I would bring into a counter. Right? You understand? My counter would count, but now I have a lot of pulses per revolution. So now instead of accounting for minutes, I could count in what? Seconds. Right? And then I'd take the number, I'd divide it by that, and then I'd do what? Divide that by 60, and that would give me the revolutions per minute. When we would do this mathematically, very easy to do. But that's what these encoders are used for. And then, of course, if I wanted to display that, then we would turn it into decimal. The problem we have with Logic Pro, and I was going to set it up on this PLC over here, is so I've got the program, but so it popped up when I was doing that TOD instruction does not work right. But you can see the applications, right? So anytime I want to display numbers to a person, I'm not going to do it in binary. I'm not going to do it in hexadecimal. We're going to have to get it in what? BCD. But all my timers are binary. All my counters are binary, right? You understand? But when we're constantly trying to give information to people, and they just don't understand binary. So that makes sense. So now you know what an encoder is.
Well, I'm thinking it's similar to the thing you showed the robotics movements in that big.
That's exactly what it is. So when we went over in operation and programming, that's what we was looking at. We was looking at an encoder, and that's what it does. It uses that to sense speed, but also it can use that to sense position. Because these things or these guys are precisely spaced apart. So they're precisely spaced apart. So if I count the number that I go, right, you understand, then I can know the exact position of the motor or whatever. So in robotics, we use the encoders for two different things. We use it to sense the speed of the motors, but we also use it to sense the position of the motor. So this is why encoders are so popular, because we can use them for two different things. Now, when I bring information in from like these guys over here. So when I go back to Logic Pro and I have these switches right here, well, watch what these switches do. So there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, that's 9. And now we're through. And what code is this? This is BCD. But if I brought these switches into my PLC and I wanted to do logic with them, I wanted to do math with them, I wanted to do all this other kind of stuff, we're going to have to get it into what phase? Binary. Does that make sense? So I bring in BCD, so it allows my operators to have BCD thumb switches, they have these BCD dials, they can punch in BCD on a keyboard on a computer, right? So if I look at my computer, it's got numbers 0 through 9. Okay, y'all understand that? So if I'm punching a number over on my keyboard, I'm punching in BCD, or it's actually a key scan code. But I need to come in and have that and convert it over to the base that the computer understands. And what base does the computer understand? They understand fine. So what we would do is we'd use the what? Yeah, we'd use that F,
From BCD.
FD, right?
Yeah,
FRD, from, okay.
From decimal.
Yeah.
From decimal to
What did I do? That's the first one I did. So now I could come up here and I could read information from decimal that the guy, so I want the motor to run at 200 revolutions per minute. Well, now I can come over here and do 200 revolutions per minute. I can compare this to my counter, right? You understand? But I need to compare it in what? In binary, right? You understand that? And if it's trying to go too fast, then my PLC can slow it down. If it's trying to go too slow, I can do what? Speed it up. Of course, we'd have to know more than what we know. But you can see we're going from a decimal world, which is what I live in, into a binary world, which the PLC lives in. So all of us have these from binary to decimal, from decimal to binary, right? So y'all understand those? Y'all okay? That makes sense? Good gracious, guys. We're going to run out of time. Degrees to radians. We talked about this a little bit. What's a radian? What's the difference between a degree and a radian?
Degree.
A radian.
Degree is the position of
Or displacement
and radius is the length.
is a length. That's exactly. So when we start dealing with actually lengths around the outside of an arc, we're dealing with radians. When we're dealing with a displacement, then we're going to be dealing with angles. So if I was a pilot, we're dealing with two different things. When you talk about vectors, vectors are an angle, but you're going to fly that angle for a certain length, right? Does that make sense? Now that would be, so the length would actually be what we're doing when we're dealing with radians, and then it would be like a vector. Are we okay? And they could mean two different things. So some PLCs give us the ability to go between radians and degrees, or degrees and radians. And you're going to deal with this a lot when you take AC, because AC is generated on 360 degrees. But a lot of times I'm not concerned with the degree, I'm concerned with how much do we have at that angle. Does that make sense?
Yeah, but we're actually talking about that sine wave.
Yeah, you're actually talking about the height of the sine waves, which would be a value, right? You understand? And not, okay, I know I get zero at 0 degrees. I get another 0 at 180. Well, what do I get at 40 degrees? What would be the output dosage at 40 degrees? Well, now we're dealing with what? We're dealing with radians. So this is why when you get into AC, a lot of your formulas are going to fall into this category right here, 2 pi rad, which is the length of the circumference. So x of L is equal to 2 pi FL. X of C is equal to 1 over 2 pi FC, excuse me. And there, so that's what we're dealing with. So now we're actually dealing with values, right, and not displacements. And these are going to cause a shift. That's going to cause what we call a phase shift. But that's when we're going to start dealing with degrees, when we talk about how much things are out of phase. So these are our two primary formulas that we use AC. So AC, if anybody tells you AC and DC are the same, just ignore them. Well, that's it on this chapter, guys. We only got one more to do, and then we're through for today. And this is, what's the next chapter? Sequence. Let me look real quick. I'll take a break. 2 minutes. I need to find that rotary sequence. Watch out. I need to look your computer off. I've been known to do that. It's a rotary sequencer that we've had in here for years, and for some reason it disappeared. I know what it looks like. So it's a drum, and it's got all these metal tabs that you can
I don't know about we take it out.
Well, they might have took it out of here to show it. And then when they got
Run it back on the
left,
track.
they just left it in the classroom. Here it is.
Okay. Yeah, that is.
Huh? That's a rotary sequence. He says vote me. Okay, I'll take a break. Get up and walk around. Okay, let's see if I got my sequencer program in here. I have no idea what we do. That is wrong. Not 5 by 6. Dang it.
I was supposed to see if I can get a quote. No, ma'am. A car. Okay, and then is Bobby Peters. UAA. His name. 135 Oxford Circle. Montreal, Alabama.